This study addresses the synthesis and thermoresponsive properties of amphiphilic copolymers composed of thermoresponsive and hydrophobic monomers, specifically DMAEMA, OEGMA300, and MMA. Understanding these polymers is crucial for advancing materials with tunable properties for biomedical and other applications where responsiveness to temperature and solvent environment is key. The approach employed here involves group transfer polymerization, a method that enables control over molecular weight and architecture, synthesizing both diblock and statistical copolymers with varying molar masses. The researchers investigate how polymer architecture and molar mass influence solubility, self-assembly, cloud point temperature, and phase transitions, providing insight into the relationship between structure and function. Monitoring techniques such as size exclusion chromatography, proton NMR spectroscopy, turbodimetry, dynamic light scattering, and transmission electron microscopy support this comprehensive study. This multifaceted approach enables a thorough exploration of how copolymer composition and structure govern their thermoresponsive behavior and self-assembly in aqueous environments. Overall, the study aims to deepen our understanding of polymer design principles needed for tailored functional materials. Figure 1 presents two important elements of the study: the chemical structures of the monomers and reagents at the top, and schematic illustrations of the group transfer polymerization (GTP) reaction process at the bottom for both diblock and statistical copolymers. The monomers used include DMAEMA, OEGMA300, and MMA, with a specific initiator, and the catalyst tetrabutylammonium bibenzoate, abbreviated as TBABB. This catalyst was synthesized following precise protocols and dried under vacuum to maintain purity. Polymerization was carefully carried out in a meticulously prepared, oxygen-free environment using dried glassware assembled on Schlenk lines and evacuated with vacuum argon cycles to prevent unwanted side reactions. The synthesis of diblock copolymers was sequential, first adding one monomer, followed by the second after reaction completion, as illustrated in the schematic bottom left. Conversely, statistical copolymers were made by simultaneous polymerization of mixed monomers, as depicted on the bottom right. Importantly, these detailed depictions highlight the chemical precision and experimental rigor needed for synthesizing polymers with well-defined architectures and compositions. Samples were taken during the process for analysis, and final products were purified by precipitation and drying. This sets the foundation for exploring how controlled polymer synthesis affects the material properties studied in later figures. Figure 2 illustrates the schematic structures of four copolymer types: DMAMA-BMMA, OEGMA300-BMMA, DMAMA-CO-MMA, and OEGMA300-CO-MMA, with an increasing experimental molar mass up to 43,000 grams per mole. The blue, light blue with dangling side chains, and red spheres represent DMAMA, OEGMA300, and MMA comonomers respectively. These polymers were synthesized with controlled compositions, fixed at 80% thermoresponsive and 20% hydrophobic weight fractions, providing a systematic platform to study the influence of molar mass on thermoresponsiveness. The high hydrophobic 20% level was chosen based on prior observations relating solubility and phase behavior limitations at higher hydrophobic content. The polymerizations were conducted using group transfer polymerization, known for its similarities to anionic polymerizations, but with advantages such as room temperature operation and rapid reaction rates. Challenges include maintaining low disparity and controlling polymerization at high molar masses, especially for OEGMA300 macromonomers, which cannot be distilled and harbor higher impurity levels. Accordingly, the disparity values ranged from 1.06 to 1.18, with higher values typically for OEGMA300 copolymers and those targeting higher molecular weights. The successful creation of polymers with varied molar masses and well-defined architecture is confirmed by chromatographic and spectroscopic monitoring. This figure serves as a visual foundation linking the chemical composition and architecture to molecular weight, key variables studied in subsequent analyses. Figure 3 displays size exclusion chromatography traces comparing diblock copolymers their homopolymer precursors, and statistical copolymers for DMA, EMA, MMA, and OE-gamma 300 MMA systems. In panel A, the dark blue lines illustrate the DMA, EMA, B MMA diblock copolymer in solid, its linear homopolymer precursor in dashed, and the statistical copolymer in dash dot style. Panel B does the same for OE-GMA 300-based polymers in light blue. The rightward shift observed in the block copolymer peaks compared to homopolymers confirms successful sequential polymerization using group transfer polymerization, indicating growth of molar mass without undesired side products or shoulders. This uniform peak shift and lack of shoulders denote narrow dispersity and clean reaction control for the DMA-EMA copolymers, reflecting high polymerization precision. However, certain OE-gamma 300 statistical copolymers show shoulder peaks at high molar mass regions, suggesting some molecular weight heterogeneity likely caused by impurities, such as polyethylene glycol dimethacrylate, leading to possible cross-linking and broader molecular weights. These results validate the successful formation of both diblock and statistical copolymers, while highlighting the complexity in controlling OE-GMA 300 polymerizations at high molar masses. Analytical techniques including SEC and 1H NMR spectroscopy provide thorough monitoring of polymer molecular weight and composition throughout synthesis. Figure 4 shows the cloud point temperatures, or TCPs, of diblock and statistical copolymers based on DMA-EMA, MMA, and OE-GMA 300 MMA, measured in both deionized water and a 95.5 volume % water ethanol mixture. The use of ethanol as a co-solvent enhances polymer solubility slightly, resulting in a small increase in TCP values compared to pure water, while preserving the relative trends. This choice is relevant for biomedical contexts where ethanol has low toxicity and is commonly used. The data illustrate that statistical copolymers consistently exhibit lower cloud points than their diblock counterparts, regardless of monomer chemistry. The authors interpret this difference as related to the poorer ability of statistical polymers to form stable self-assembled structures, like micelles, in solution, compared to block copolymers. For DMA-EMA-based copolymers, measurements were conducted at natural pHs around 9.2 to 9.4, with additional pH-controlled studies discussed separately. The plots highlight how increasing molar mass influences TCP, informing on the effects of molecular weight and polymer architecture on thermoresponsive behavior. This figure underscores the interplay between polymer structure, solvent environment, and thermally induced phase transitions, crucial for tailoring polymer applications. Figure 5 provides a schematic illustrating how OE-GMA 300/MMA random copolymers can self-assemble in aqueous solution into uniform nanoparticles. In the diagram, blue lines depict the polyethylene glycol side chains grafted on OE-GMA 300 units, while red lines indicate the hydrophobic methyl side groups on MMA comonomers. The black line represents the methacrylate polymer backbone. This self-assembly arises from the amphiphilic nature of the random copolymer and its tendency to adopt folded conformations in water. The authors interpret this behavior as formation of unimer micelles, where polyethylene glycol side chains shield hydrophobic segments folded within the structure, yielding colloidally stable, uniform nanoparticles resembling core shell architectures. In contrast to DMA-EMA-based random copolymers, which mostly remain as random unimers without micelle-like folding and show different thermoresponsive behavior, the OE-GMA 300 random copolymers' ability to fold into stable nanostructures influences their cloud point properties. This represents a key insight into how polymer chemistry and architecture shape nanoscale self-assembly and thermal response. Understanding these assemblies helps explain differing experimental observations and guides rational design of thermoresponsive materials. Figure 6 examines how the cloud point temperature of DMAMA-based diblock and statistical copolymers changes with pH, highlighting the influence of protonation from the tertiary amine groups in DMAMA. Measurements were performed visually and verified by turbidimetry, with error bars representing plus or minus 1 degree Celsius, reflecting typical method precision. Importantly, some diblock polymers did not exhibit a measurable cloud point within the studied pH range. And high molar mass polymers D1, D2, and D4 were excluded due to insolubility above pH 8. The pKa values for these polymers are narrowly distributed between 7.3 and 7.5, consistent with literature, implying protonation states critically affect solubility and thermal response around physiological pH. The degree of protonation was calculated based on these pKa values and titration data, showing strong pH dependence. These findings emphasize that the design of thermoresponsive polymers must consider not only polymer architecture and molecular weight, but also environmental pH, which modulates protonation and thus phase behavior, crucial for applications involving biological fluids or variable pH conditions. Figure 7 presents transmission electron microscopy images of copolymers with both the highest and lowest molar masses from each copolymer series, comparing block and statistical architectures. The samples were prepared as 1% weight polymer solutions in deionized water and negatively stained for enhanced contrast. The scale bar indicates size, and measurements were quantified via ImageJ software, with approximate particle sizes labeled on each image. The top row displays diblock copolymers DMA EMA 162 B MMA 64 D3, DMA EMA 28 B MMA 10 D13, OEGMA 30037 B MMA 28 05, and OEGMA 3009 B MMA 5 013. The bottom row features corresponding statistical copolymers with similar monomer compositions but random architecture. These micrographs reveal differences in morphology attributable to architecture and molar mass. The diblock copolymers tended to form spherical core shell micelles, whereas statistical copolymers showed more coil-like or less defined structures. This morphological evidence complements scattering and thermal data, confirming that polymer structure critically influences nanoscale assembly, which in turn governs solubility and thermoresponsive characteristics. Such microscopy data provide direct visualization of polymer solution states, pivotal for understanding and applying these materials. Figure 8 presents schematic models contrasting the two extreme polymer chain configurations relevant to this study. The amphiphilic core shell micelle, typical of diblock copolymers, versus the random unimer coil, characteristic of statistical copolymers. Illustrated using DMA, EMA, and MMA as examples, the core shell micelle displays a hydrophobic MMA core, shown as red circles, surrounded by a corona of hydrophilic DMA, EMA units, represented as blue circles. This architecture arises from amphiphilicity driving microphase separation in aqueous solution. Conversely, the random coil model depicts a chain with mixed hydrophobic and hydrophilic units, without phase separation, characteristic of statistical copolymers that do not self-assemble into micelles. These models guided interpretation of dynamic light scattering data and provided a framework to understand differences in particle size and morphology observed experimentally. For block copolymers, calculations based on polymer degrees of polymerization and assumptions about chain stretching and hydrophobic domain overlap predicted sizes generally larger than experimentally measured hydrodynamic diameters, but consistent overall. For statistical copolymers, random walk models estimated coil sizes that mostly matched experiments, except for OEGMA 300 co-MMA polymers, where self-assembly into unicore micelles is suspected. These visual frameworks emphasize how polymer architecture fundamentally influences solution behavior and nanoscale structure. Figure 9 plots the experimentally measured hydrodynamic diameters, DH, of DMA-EMA, MMA, and OEGMA 300 MMA copolymers as a function of molar mass across different polymer architectures. The majority of measurements were conducted at 20 degrees Celsius, except DMA-EMA statistical copolymers measured at 10 degrees to ensure solubility. Both block and statistical copolymers show an increasing hydrodynamic diameter with increasing molar mass, following the expected trend. However, block copolymers tend to form defined micelles with diameters ranging roughly between 10 and 50 nanometers, consistent with theoretical predictions based on chain length and polymer configuration. Statistical clay polymers generally exhibit smaller sizes, reflective of coil conformations, except for the OEGMA 300 co-MMA series, which shows systematically larger diameters than predicted. This discrepancy is interpreted as arising from OEGMA 300 co-MMA polymers' ability to self-aggregate into unicore micellar structures and the bulky polyethylene glycol side chains, which are not accounted for in simple coil size models. Overall, the experimental and theoretical comparisons demonstrate the strong influence of polymer chemistry and architecture on nanoscale size and assembly, supporting the structural models previously discussed. Figure 10 illustrates the phase behavior and rheological properties of a high molar mass DMA-EMA-B-MMA diblock copolymer, D3, in aqueous solution. Panel A shows a phase diagram constructed from visual observations at varying temperature and polymer concentration. 4 distinct phases were identified: runny solutions, viscous solutions, gel formation, and eventual two-phase separation, displayed in white, red, blue, and green colors respectively. At polymer concentrations exceeding 15% by weight, D3 forms a cloudy gel in the range of 28 to 30 degrees Celsius. This gel undergoes syneresis, where water is expelled from the network, causing visual destabilization, eventually leading to phase separation as temperature rises further. Panel B provides rheological data confirming gel formation at 20 weight % concentration. The storage modulus G' and loss modulus G', cross twice during heating, indicating transitions between sol and gel states as well as onset of precipitation at higher temperature. The maximum observed storage modulus of 101 Pascal seconds suggests relatively weak physical entanglements within the gel network. The cloudy nature of the gel versus transparency indicates collapse of the hydrophilic corona chains preceding gelation, promoting micelle aggregation and network formation. Notably, D3 was unique in exhibiting a sol-gel transition among the tested copolymers, highlighting the combined influence of molecular weight and polymer architecture on phase behavior. In conclusion, this study comprehensively explores the synthesis and thermoresponsive properties of amphiphilic diblock and statistical copolymers based on DMA-EMA, OEGMA 300, and MMA. Employing group transfer polymerization, the authors successfully produced polymers with controlled composition and a broad molar mass range, up to 43,000 grams per mole. The copolymers' molecular weight and architecture markedly influence their thermoresponsive behavior, solubility, and self-assembly in aqueous environments. Diblock copolymers consistently formed micelle-like core shell structures with higher cloud point temperatures compared to statistical copolymers, which tended to remain as random coils or unimer micelles depending on chemistry. The use of ethanol as a cosolvent enhanced solubility and allowed accurate cloud point measurements. pH strongly affected DMA-EMA-based polymers owing to their protonatable tertiary amine groups, emphasizing environmental sensitivity. Transmission electron microscopy and dynamic light scattering confirmed morphology predictions and particle size trends. The unique gelation behavior observed in a high molecular weight diblock reveals opportunities and limitations for application development. Overall, the findings highlight the critical roles of polymer architecture, molecular weight, monomer chemistry, and solution conditions in dictating functional thermoresponsive polymer properties, offering valuable design guidelines for advanced material synthesis.